Hey, my friends. Hello, friends. Hello, friends. IBM is here to record the part 4 of work, energy, and power. Uh, this is part 4 of work, energy, and power multiple choice questions. Cambridge Physics AS 9702. I think we stopped on page. 56. Maybe 46. I'll just scroll to page 46. Okay, I think we stopped here on page 46. We are going to page 47. So without wasting time, let's just move to page 47. Okay, in part 4, we are starting on from page 47. A fisherman lifts a fish of mass 250 grams from rest through a vertical height of 1.80 meters. The fish gains speed 1.1 meters per second. What is the energy gained by the fish? Okay, so the fish gains a speed of 1.1 meters per second, but is lifted through a vertical height of 1.8 meters. So it means the energy gained by the fish is going to be the kinetic energy plus the potential energy. So this will be for kinetic energy to be a half times the mass, which is 250, times 10 power negative 3, times the speed, which is 1.1 squared, plus for the potential energy to be mgh, which will be the mass, that is 250, times 10 power negative 3 times g, which is 9.81, times h, which is 1.8. So I'll just press my calculator. So this is going to be 0.5 for a half times 250 exponent negative 3, then times 1.1 squared, which gives us 0.15 plus. For the other one is 250 exponent negative 3 times 9.81 times 1.8, which gives us 4.41. And when we sum up 4.41 plus 0.15, we get 4.56, or approximately 4.6. So this is 4.6 joules, which makes our answer to be D. Water from a reservoir is fed to the turbine of a hydroelectric system at a rate of 500 kilograms per second. The reservoir is 300 meters above the level of the turbine. The electrical output from the generator driven by the turbine is 200 amperes at a potential difference 6,000 volts. So this is the electrical output. So what is the efficiency of the system? We now know that efficiency is equal to the power output. So this will be the power output over the power input, and we multiply this by 100 to change to percentage. So this is therefore going to be the power output. Of course, that will be I times V. That is the power output. But then for the energy power input, the power input will be the work done. Power input will be equal to the work done per unit time of moving the turbine. Of moving the water through that vertical height, which will be mgh divided by t. But they have given us m over t as 500 seconds. So this will be divided by mgh over t. So I'll substitute. This will be 200 times v, which is 6,000, divided by m over t, which is 500, times g, which is 9.81, then times h, which h is 300 meters. Then I'll multiply this by 100 to make it percentage. So this is 200 times 6,000 times 100 to make it percentage, divided by 500 times 9.81 times 300, which gives us 81.5 1.5, which is approximately 82%. So this is 82%. So our answer is going to be D, 82%. A loaded aeroplane has a total mass of 1.2 times 10 power 5 kilograms while climbing after takeoff. It climbs at an angle of 23 degrees to the horizontal with a speed of 50 meters per second. What is the rate at which it is gaining potential energy at this time? Of course, rate of gain of potential energy is power. So power will be equal to the work done over time taken. Power can also be force times velocity. So what is the rate at which it is gaining potential energy at this time? So the force, because it's moving at an angle and the velocity is constant, because it's moving with a horizontal speed of 50 meters per second, so it means it's climbing with the same speed. So since the velocity is constant, so it means the resultant force along the plane is going to be zero. Remember how we have been dealing with objects along the plane. It is moving, it is climbing with a constant velocity. That means the force upwards and the force downwards are equal. But we can get the force downwards from the component of the weight down the slope, which we have already seen that is always sine, weight sine theta. So this is going to be equal to weight, which is mg sine theta, then times v. So when we substitute, this will be m, which is 1.2 times 10 power 5 times g, which is 9.81 sine of 23. Then we multiply this one by v, which v is 50. And then I press my calculator. 1.2 exponent 5 times 9.81, then sine 23, then times 50. So this is giving us 22,998. So 22,998,000 joules per second. So they have given us these two significant figures. So this will be 2.3 times 10 power 6 joules per second. So it means our answer is it power 6? No, 337. So this is power 7. So the answer is going to be C. 2.3 times 10 power 7 joules per second. When a horizontal force F is applied to a frictionless trolley over a distance S, the kinetic energy of the trolley changes from 4 joules to 8 joules. If a force of twice F is applied to the trolley over a distance of 2s, what will be the original kinetic energy of 4 joules become? So remember the change in kinetic energy. The change in kinetic energy is going to be equal to the work done. And the work done is force times distance in the direction of the force. So for the first case, we have that 8 minus 4, that is the change in kinetic energy, is equal to the force was F and the distance was S. For the second case, the kinetic energy is not known, but the original is 4. The final kinetic energy is not known, but the original is 4 minus the force is twice F. So this is equal to 2F times the displacement, which is twice S. So we have to combine these two equations. So I will say EK minus 4 divided by 8 minus 4, which is 4, is equal to 4Fs divided by Fs. So Fs has cancelled out. So it means EK is going to be 4 times 4, which is 16, plus 4, that is 20 joules. So the answer here is going to be B. In normal driving conditions, an electric car has a range of 150 kilometers. This uses all of the 200 megajoules of energy stored in its batteries. When the batteries initially fully charged, the car is driven 100 kilometers in normal driving conditions. So how much energy is this? Of course, we have answered such a question earlier on. If the car is driven 100 kilometers, then we can say the energy used here is simply going to be 100 kilometers over 150 times 200 megajoules. So this will be 200 megajoules. And I think this one gives us 400 divided by 3 megajoules. That is the energy used. But remember, energy is equal to power times time. which is going to be I times V times T. So they told us that the batteries are then recharged from a household electrical supply, delivering a constant current of 13 amperes at a potential difference of 230 volts. So the energy of 400 over 3 times 10 power 6 should be equal to the current, which is 13.0, times V, which is 230, times time. What is the minimum time required to recharge the batteries? So we want T. So we just press the calculator to find T. So I have 400 divided by 3. Or I can say 400 exponent 6 divided by 3 divided by 13 times 230. So that is 44593. 44593 seconds. And we want this time in hours. They have given us in hours. So 44593 divided by hours, 3600 to change it to hours. So this is divided by 3600, which is 12.4. So this is 12.4 hours. So which makes the answer to be B. In which situation is no work done? In which situation is no work done? The air in a bicycle tire is released because of a puncture. So there is work done. Reason, the air will be pushing against the atmosphere, so there is work done there, which is pressure times change in volume. A ball is dropped and falls to the ground. A ball is dropped and falls to the ground. Of course, there is force due to gravity pulling it downwards, and it is moving a distance, so there is work done there. A box moves at a constant speed, that means the change in kinetic energy is equal to 0 across a smooth surface. It moves at a constant speed. So it means the work done is going to be, because there is no change in kinetic energy, V is constant. This means acceleration is equal to 0. The resultant force is 0, so there is no work done. So the work done is equal to change in kinetic energy, which is going to be 0. So here there will be no work done. So the answer is going to be C. A crane lifts a steel girder at constant speed. So it is lifting at constant speed. So that means there is no change in kinetic energy. However, work is done against gravity, so there is gain in potential energy. So it means there is work done here because of potential energy. But because in part C it was moving across a horizontal smooth surface, then there is no gain in potential energy, there is no change in kinetic energy, so there is no work done there. An electrical railway locomotive has a maximum mechanical output of 4 megawatts. Electrical power is delivered at 25 kilovolts from overhead wires. So this is delivered. The overall efficiency of the locomotive in converting electrical power to mechanical power is 80%. What is the current from the overhead wires when the locomotive is operating at its maximum power? So first of all, we know that power is going to be I times V. And we also know that efficiency is going to be equal to efficiency, which is 0.80, is going to be the power output divided by the power input. But an electrical railway locomotive has a maximum mechanical output power of 4 megawatts. That is the output. So the output is 4 megawatts, 4 times 10 power 6, divided by the power input. Electrical power is delivered at 25 kilovolts from overhead wires. So from wires we can get the input, and the input is going to be the current times the V. So this will be 25 times 10 power 3, then that is V, then times the current I. So we are trying to find I. So I is going to be equal to, I'll just press my calculator. Efficiency, so I'll just say 4 exponent 6 divided by, open brackets, 0.80 times 25 exponent 3. So this is giving me 200. The 200, let me repeat, 4 exponent 6 divided by, open brackets, 0.8 times 25 exponent 3. So this is giving me 200. So this is 200 amperes. So this means our answer is going to be A, 200 amperes. An object of weight 15 newtons, is pulled along a horizontal surface at a constant velocity of 2 meters per second. The force pulling the object is 12 newtons at 30 degrees to the horizontal. What's the power used to move the object? So we know that power is equal to force times velocity. The velocity is 2 meters per second, but the force, we have of course to resolve this force in the direction in the direction of motion. So the work done, so that the work done is equal to force times distance in the direction of the force. So the force is going to be 12 cos 12 cos of 30. Why do I want I find for power? Let me just say, okay, the work done is 12 cos 30 times the distance. The force pulling the object 12 newtons at 30 meters at 30 degrees to the horizontal as shown. An object of weight 15 newtons, so the 15 newtons will not have an effect on the work done, is pulled along a horizontal surface at a constant velocity of 2 meters per second. That is the velocity. The force pulling the object is 12 newtons at 30 degrees to the horizontal as shown. So the force is 30. The force which causes motion is going to be 12 cos 30. So here I will just say, okay, I will not mind about work done. I'll just find the force causing motion in the horizontal and I find the power. So power is going to be force times velocity. So power is going to be 12 cos 30, then times the velocity, which is going to be 2. So 12 cos of 30, then times 2, which is going to be 20.8. So this is going to be 20.8 watts. So the answer is going to be B. What is the average power output of a laser that can deliver 0.2 joules in 10 nanoseconds? So power is going to be equal to energy over time, which energy is 0.2 divided by time, which is 10 times 10 power negative 9 because it is nano. So this is 0.2 divided by 10 exponent negative 9. So that is 2, I think it is 20,000, 20 millions. So this is 20 millions. So this is 20 millions, which is 20 megawatts. So the answer is going to be D, 20 megawatts, not milliwatts, megawatts. The engine of a car exerts a force of 600 newtons in moving the car 1 kilometer in 150 seconds. What is the average output power of the engine? So power is equal to work done over time taken. And the work done is force, which is 600 times the distance, which is 1 kilometer, that is 1000, divided by time, which is 150. And this, I think, gives you 4000. 600 times 1000 divided by 150, that is 4000. So this is going to be 4000 watts, and this is the same as 4 kilowatts. So the answer is going to be B. You notice that as we advance towards the end of this document, the questions become more direct because Cambridge goes on evolving. So all the first questions or the earlier questions were simpler. A mass at point X inside a uniform gravitational field experiences a gravitational force of 0.2 newtons. Note that the gravitational force acts in the direction of the field, so the force due to gravity is in the same direction as the field. It has 1.0 joules of gravitational potential energy, that is at X. So potential energy here is going to be 1. A mass at point X inside a uniform gravitational field experiences a gravitational force of 0.2 newtons. It has 1 joule of gravitational potential energy. So this is 1 joule. The mass is then moved to point Y. The mass is then moved to point Y. What is the new gravitational potential energy? So when it is moved to point Y, the work done here is going to simply be equal to the gain or the change in potential energy, which is simply going to be the change in potential energy from X to Y is going to be um, the mass times G by H, but H is going to be the distance in the direction of the field, because the force for work to be done, the force must be in the same direction as the field. So this is going to be mg is 0.2 newtons, and then H is going to be 30, which is 0.3, and this gives us 0.6 joules. So that's the work done to move from X to Y. So the new potential energy now is going to be 0.6 plus 1, which gives us, no, is it 0.6? 0.2 times 0.3 is 0.06. So there's a 0 here. So this will be 0.06 plus 1, which is 1.06 joules, which makes the answer to be C. A small mass is placed at a point P on the inside surface of a smooth hemisphere. It is then released from rest. It is released from rest. When it reaches the lowest point T, its speed is 4 meters per second. The diagram, not to scale, shows the speed of the mass at other points Q, R, and S as it slides down. Air resistance is negligible. Air resistance is negligible. The mass loses potential energy E in falling from P to T. It loses potential energy. At which point has the mass lost potential energy E over 4? Now we notice if air resistance is negligible, let's also neglect effect of friction. Then that means the potential energy lost, not power, potential energy lost at a point, at any point, must be equal to the kinetic energy at that point. The potential, because it was released from rest, the potential energy lost at a point must be equal to the kinetic energy at that point, because it was released from rest. Initial kinetic energy was 0. So that is, since the mass is at rest at P, because it was released from rest at point P, that means at any point, the potential energy lost at that point must be equal to the kinetic energy at that point. So let's try to see this. So if they said the mass loses potential energy E in falling from P to T. So when it reaches the lowest point, its speed is that. So the potential energy at P must be equal to the kinetic energy at T. That one is obvious. So potential energy, E potential at, what should I use? Let me use PE. So potential energy at P should be equal to the kinetic energy, or the potential energy, or let me say the potential energy lost falling from P to T must be equal to the kinetic energy of the mass at T. Potential energy lost. Potential energy lost from P to T should be equal to the kinetic energy of the mass at T. Let's see what is that potential energy. This means, because the speed at T is 4 meters per second, then that means the potential energy which has been lost, this is going to be a half times mass times the speed at T squared, which is going to be a half times m times speed at T squared, which is going to be 4. That is going to be 4 squared. And I think this gives us 16 over 2, which is 8 m in joules. Not millijoules, it is 8 m, or m times 8 in joules. That is the potential energy which must have been lost as it was moving from P to T. So this is the kinetic energy at T, and it is the potential energy which has been lost. Okay, so at rest at P, kinetic energy was 0. Note that very carefully. At P, when it was at rest, kinetic energy was 0. And what was the energy, total energy there was only potential energy, which we have got as 8 times m joules. 8 times m joules. That is at P. So it means when E, this question is at which point has the mass lost potential energy E over 4? At which point has the mass lost potential energy, which is E over 4? Note that at T, it will have lost potential energy, which is 8m. So total energy there was 8m, and when potential energy lost is equal, when potential energy lost is E, or let me just say E over 2, potential energy lost of E over 4 is the same as 8m. 8 times m divided by 4, which is equal to 2m joules. 2 times m joules. It is 2 times m joules. So E over 4 is the same as 2 times m joules. That is the potential energy which has been lost. Note very carefully that at Q, for example, at Q, the kinetic energy is equal to a half times the mass m times the speed, which is 1 squared. And this gives us 0.5 times m joules. So this is the same as potential energy which has been lost from P to Q. Then we can check at R. At R, the kinetic energy is equal to a half times m times the speed, which is 2 squared. And this automatically gives us 2m joules. So the question was, at which point has the mass lost potential energy E over 4? We are seeing that E over 4 is equivalent to 2 millijoules, and we are seeing that at R, the kinetic energy is 2 millijoules, 2 times m joules. And we said initially that the potential energy lost from P to T is equal to the kinetic energy of the mass at T. That means since the mass started from rest, the potential energy lost to reach any point must be equal to the kinetic energy at that point. Therefore, the point we are looking for here is going to be R, because the kinetic energy at that point is 2 times m joules, and this is going to be equal to the potential energy which has been lost. And 2m joules is the same as E over 4. So that means our answer here is going to be R. It's quite tricky. A uniform solid cuboid of concrete of dimensions 0.5, 1.2, 0.4, and weight 4,000 newtons rests on a flat surface with 1.2 meter edge vertical as shown in the diagram. Okay. What is the minimum energy required to roll the cuboid through 90 degrees? It is to be rolled. It is to be rolled through 90 degrees to the position shown in diagram 2 with at the 0.5 meter edge vertical. So I want us to notice that if we try to roll this, initially its center of gravity, the center of gravity of this is along a line which is at the center here. Now, if we try to roll it, I'll just take off one plane, which is the one which is a rectangle. So let's try to roll this off by raising it through. Let's say it is now in this position here. It is now in this position here. I want to put it in the highest position possible. So let's say it has been raised so that it is now in the highest position during the roll. It is now somewhere here. So this has been slightly raised to the highest point. I don't know how I can draw this so that it is vertical. So the vertical line through the, let's say this vertical line through the center of gravity reaches here, this point here. When it has been, remember the vertical line was initial along here. Now if it has been raised, the highest point this can be is this point here. Okay, so if initially this was at 0. I think this is 0.6 initially. This was at 0.6 meters. So when we flip it, it raises to a certain value. So the center of gravity raises higher, a little bit higher to a certain value. Let's first get the this distance here, this diagonal here. That diagonal can be got from Pythagoras theorem. Remember the length here is 1.2 meters and the horizontal is 0.5 meters. So it means this diagonal line here is going to be the square root of, using Pythagoras theorem, to be 1.2 squared plus, that is 1.2 squared plus 0.5 squared, which gives us, that is 1.2 squared plus 0.5 squared, square root of the answer, that is 1.3. So this is 1.3 meters. So the diagonal is 1.3 meters. What does that mean? It means the position of the center of gravity. Center of gravity is going to be at 1.3 divided by 2, which is going to be, I think this is 0.65 meters. So when it is being rolled, it means the center of gravity raises to 0.65, yet it was initially at 0.6 meters. So we can now find a change in, because the question wants us to find what is the minimum energy required to roll the cuboid through 90 degrees to the position shown in the figure. So when it is, the change in energy there is going to be equal to, so the change in energy when it is rolled is going to be equal to mg times the change in the value of height, or the change in the height of the center of gravity. So this is going to be equal to mg is 4,000, but when it is being rolled, the highest it goes to is at up to 0.65, and it changes from 0.6 meters. That is the position of the center of gravity. So this will be 0.65 minus 0.6 meters. So I think this gives us 0.65 minus 0.6 times 4,000. I think that is 200 joules. So this is 200 joules. So it means the minimum amount of energy required to roll the cuboid through 90 degrees to the position shown in the diagram is going to be 200 joules. So the answer is going to be A. An electric motor has an input power P in, useful output power P out, and efficiency nu. We can look at that demonstration: power in, power out, power lost, and efficiency nu. How much power is lost by the motor? How much power is lost by the motor? So I think this is easy mathematics. So number one, we know that efficiency nu is equal to the power output divided by the power input, which means if I make power input the subject, the power input is going to be equal to power output divided by nu. How about power lost? Because the question is how much power is lost. We also know that power lost is going to be power input minus power output. The power lost is power input minus power output. But power input is P out over nu, so I'm just going to substitute. So power lost is where there is power input, I'll put P out, divide by nu, then minus P out. So I just divide both sides by P out. So when I divide by, sorry, when I simplify this by dividing this by P out, I remain with 1 over nu minus P out over P out, which will be 1. Then I can factor out P out. Alternatively, if that mathematics is very hard for n of us, there's a common factor there, which is P out. So I'll simply say P out is common factor. So in brackets, I remain with 1 over nu, then minus 1. So this means our answer is automatically going to be D. P out, P lost, power lost is going to be 1 over nu minus 1 times P out. That's just algebra. A mass attached to the lower end of a spring bounces up and down. At which points in the path of the mass do the gravitational potential energy of the mass, the elastic potential energy in the spring, and the kinetic energy of the mass have their highest values? To begin with, kinetic energy is maximum. Kinetic energy is maximum when V is maximum, and V is maximum at equilibrium position, that is at the midpoint of oscillations, at the middle point. So it means kinetic energy is maximum at the midpoint. Let's check kinetic energy. So we eliminate A and D, because if this is the equilibrium position and a mass which has been attached on a spring, there is a mass which has been attached on a spring, so it will go downwards and can also move upwards. So at equilibrium, it passes here with the maximum velocity. So it means kinetic energy is maximum at the midpoint. If it moves downwards, the spring stretches, the elastic potential energy becomes maximum at the lowest point, or elastic potential energy is maximum at the highest point, because elastic potential energy is equal to a half kx squared. So when x is maximum at the lowest point or at the highest point, then elastic potential energy is maximum. So for elastic potential energy, we look at the top or at the bottom. So B and C has both top and bottom, so we can't use that column for answering. Then gravitational potential energy is equal to mgh. So it depends on h, which h in this case will be the displacement x. So gravitational potential energy is maximum, but this gravitational potential energy is maximum at the top, not at the bottom. So for gravitational potential energy, it is maximum at the top, not at the bottom. So we ignore B, so our answer becomes C. A small electric motor is mounted on a bench as shown. The motor is connected to a 6-volt supply and the current in the motor is 0.5 amperes. The motor is 50% efficient. The motor is 50% efficient. What is the time taken to lift a mass of 200 grams up through a height of 90 centimeters? Okay. So we are looking for time. So they gave us efficiency of 50%, and we know that efficiency is equal to the power output divided by the power input. The efficiency is 0.50. The power output is the motor is connected to a 6 volts supply and the current in the motor is 0.5. What is the time taken to lift a mass of 200 grams? So it means this is going to be the output. Lifting 200 grams through a height of 90 centimeters must be the output. So this is going to be power input. So this is going to be, let me just write power output over power input. The power input is going to be I times V. Power input will be I times V, which is going to be 0.5 times V, which is 6. That is the power input. And then the power output is going to be lifting this mass, so it will be doing work against gravity, so that is mg times h divided by t. That is the power, that is going to be the power output. So let me just substitute this in this equation of efficiency. So we have that 0.50 is equal to the power output, which is m. M is 200 grams, which is 0.2. G is 9.81. The height is 90 centimeters, which is 0.9. Divide by time t, that is the power output. This is divided by the power input, which is 0.5 times 6. So I'm just going to make t the subject from my calculator. 0.5 times 0.5 times 6. So I'm just going to divide 0.2 times 9.81 times 0.9 with the answer I got to make t the subject. So this is giving me 1.17. So t is 1.1772 seconds just by cross multiplying and making t the subject, which is approximately 1.2 seconds. So it means my answer is going to be C. A projectile is launched at 45 degrees to the horizontal with initial kinetic energy E. Initial kinetic energy is E. Assuming air resistance to be negligible, what will be the kinetic energy of the projectile when it reaches its highest point? Kinetic energy when it reaches its highest point. Okay, so this is combining concepts of projectiles with work energy and power. So I'll just use, remember the velocity in the horizontal does not change. Let's think of a projectile. Let me take you back to projectiles. It is projected, it is launched at an angle of 45 degrees. So if the velocity here is v, then the velocity in the horizontal is going to be vx, is going to be v cos of 45. That is the velocity in the horizontal. At the highest point, velocity in the vertical becomes 0, so it is only velocity in the horizontal which is acting, which is v cos 45. So it means, and we also know that kinetic energy Ek is a half mv squared. So at the highest point, I've said velocity is equal to 0, so energy due to the vertical component of velocity is 0. And you note that kinetic energy, of course, a half m will be constant, or you can consider it still. So kinetic energy in the x is simply going to be a half times m times the velocity in the x, which is simply going to be v cos 45 squared at the highest point where velocity in the vertical becomes 0. So this is giving us the kinetic energy at the highest point, which is a half m v cos squared. But remember, a projectile is launched at 45 degrees to the horizontal with initial kinetic energy E. The initial kinetic energy, which is E, should be equal to a half m times the initial velocity, which is v, but squared. And assuming air resistance to be negligible, what would be the kinetic energy of the projectile while it reaches its highest point? So we are going to just combine these two equations. Let me first simplify the kinetic energy at the highest point. Let me use this h. So because at the highest point, the kinetic energy is only in the x, is due to the velocity in the x. I think cos 45 squared is the same as a half, I think. Is it a half? Let me check. Cos 45 squared is a half, okay? So this becomes a quarter, I think, or it becomes, okay, a half m times 0.5 v squared, because cos 45 squared is a half, so that is 0.5. So I'm just going to divide these two equations because we want what will be the kinetic energy of the projectile when it reaches its highest point. So at the highest point, kinetic energy is a half m times 0.5 v squared. But remember, a half m times v squared is E. So this becomes 0.5 times E. So this means my answer is going to be A. initial kinetic energy was E, which is a half mv squared, but at the highest point the velocity is only due to the horizontal, which is v cos 45. That's what gave us 0.5 v squared when we squared it. And when we factor out a half mv squared, a half mv squared is going to be E, so our answer is 0.5 E. A constant force F acting on a car of mass m moves the car up a slope for a distance s at a constant velocity v. The angle of the slope to the horizontal is alpha. Note that the velocity is constant. That means there is no resultant force acting on this car. So the force up the slope is the same as the component of the weight down the slope. Which expression gives the efficiency of the process? So let's see the work input. The work input is simply going to be moving the force F times the distance s. That is the work done in moving this up the plane. The force times the distance. That is the work input. But the work output is going to be the work done in the vertical to overcome the weight. The work output is going to be equal to the gain in gravitational potential energy, which is going to be mg times h. We can find h. This is the height h. And you notice that sine of alpha is equal to h over s. So it means h is s times sine alpha. So this becomes mg times s sine of alpha. So let's find efficiency. Efficiency is equal to work output, the useful work output over the total work input. So this would be mg times s sine alpha divided by f times s. So s cancels out. So we remain with mg sine alpha divided by f. So meaning our answer is going to be D. A van driver adjusts the force on a van's brakes so that the van travels at constant speed down a hill from P to Q. The magnitude of the change in the van's kinetic energy is delta EK, and the magnitude of the change in the gravitational potential energy is delta EP. Which statement is correct? Which statement is correct? Okay. So of course, kinetic energy is constant. Kinetic energy, sorry, the speed is constant, so kinetic energy is constant, so the change in kinetic energy is equal to 0. The change in kinetic energy is 0 because the speed is constant, so automatically the answer is D. The change in kinetic energy is 0 because the speed is constant without even wasting time. A ball of mass 400 grams shoots an arrow of mass 120 grams vertically upwards. The potential energy stored in the ball just before release is 80 joules. Before release, it is 80 joules. The system has an efficiency of 28%. The system has an efficiency of 28%. What is the height reached by the arrow when air resistance is neglected? So remember, efficiency is going to be the useful energy output or power output. Okay, the useful energy output over the energy input. So the efficiency is 28%, which is 0.28. What is the energy output? Energy output would be to move the system or to move the mass of 120 grams, to move the mass of 120 grams upwards. So this is going to be M, because energy output is going to be mgh, and the energy input is 80 joules. So this is going to be M, which is 120 times 10 power negative 3. Then, because that is the mass which is going to be moved vertically upwards by the arrow which has shot it. So this is 120 times 10 power negative 3 times 9.81 times h. then divide by the energy input, which is 80 joules. The potential energy stored in the ball just before release is 8 joules. So that is what is put in to raise the arrow upwards. So we are now finding H. I'll just say 0.28 times 80 divide by open brackets 120 exponent negative 3 times 9.81. So this is giving me 19.0, which means H is approximately 19 meters. So the answer is going to be B. Somebody may be asking, why didn't I use 400 grams? Why didn't I use 400 grams? They said air resistance is neglected. That means you would also use conservation of energy. But since they gave us efficiency, it was easier to use efficiency. The energy output would be to raise the arrow of mass 120 grams upwards. That's what we aim at. That is the work done by the ball. So the mass of the ball does not contribute to raising 120 grams vertically upwards. However, it is the energy which is put into it that contributes to raising 120 grams vertically upwards, but at an efficiency of 28%. That's why I ignored the mass of the ball itself. A train on a mountain railway is carrying 200 people of average mass 70 kilograms. So every person is about 70 kilograms up a slope at an angle of 30 degrees to the horizontal and at a speed of 6 meters per second. So the speed is constant, 6 meters per second. The train itself has a mass of 80,000 kilograms. The percentage of the power from the engine which is used to raise the passengers and the train is 40%. So the efficiency is 40%. What is the power of the engine? What is the power of the engine? So let's begin. That is the power input. We want to find the power input. So we know that efficiency, which is 0.4, should be equal to the power output over the power input. So the power output would be to raise these people, the 200 people, plus the mass of the train itself. That would be the power output. It would be the work done to raise 200 people plus the mass of the train itself. But remember, the train is, the angle of incline of the slope is 30 degrees. So since the speed is constant, then the component of the weight down the slope will be the one we are trying to overcome there. So it will be the force. So power is also equal to force times velocity. So I'll say the efficiency of 0.4 is equal to power output, which will be the force, which is 200 times each person, which is 70, then plus the mass of the train itself, which is 80,000. That is the mass, total mass, times G, which is 9.81. I'm using mg. I'm using F equals to mg. That is the weight. So that's why I have the total mass times G, that is the force, then times the velocity, which is, oh, by the way, we have to resolve this. So this would be sine of 30. Then we multiply this by the velocity, which velocity is 6.0. Then divide by the power input, which is going to be now the total power produced by the engine. So using the calculator, I'll just get the power in 200 times 70 plus 80,000 sine times sine of 30, then times 6, and I will divide this by 0.4. And this is giving me, I don't know that this is correct. Let me repeat it again. Have 200 times 70 plus 80,000 then times 9.81 sine of 30. So I'll multiply this by 6. Then I divide this by 0.4. So this is giving power in as 6916050. So the power in is equal to 6916050. 6916050. So they have given us answers in terms of mega, so I will divide this by 10 power 6, which means 1, 2, 3, 4, 5, 6. So this is going to be 6.9 megawatts. So the answer is going to be C. A gas is enclosed inside a cylinder which is fitted with a frictionless piston. Initially, the gas has a volume V1 and is in equilibrium with the external pressure P. The gas is then heated slowly so that it expands, pushing the piston back until the volume of the gas is increased to V2. How much work is done by the gas? So change in volume is equal to V2 minus V1. Remember, work done is equal to pressure times change in volume. So this will be pressure into V2 minus V1. So the answer is going to be A. A solid rubber ball has diameter of 8 centimeters. It is released from rest with the top of the ball 80 centimeters above a horizontal surface. So the top of the ball is 80 centimeters above the horizontal surface. It falls vertically. It falls vertically and then bounces back up so that the maximum height reached by the top of the ball is 45 centimeters as shown in the diagram. So let's first of all initially look at where this distance here. The diameter of the ball is 8 centimeters, but starts from 8. So it means when we are finding gravitational potential energy, the starting point is going to be 80 minus 8, which is going to be 72 centimeters. So the gravitational potential energy will be considered by looking at 72 centimeters, not 80 centimeters. Then when it returns, we also look at it from the bottom, because it comes back to 45, yet the diameter is 8, so this distance is going to be 45 minus 8, which is I think 37 centimeters. It will be 37 centimeters from the bottom or from the ground. So potential energy at the bottom of the ball at release must be equal to the kinetic energy of the bottom of the ball just before striking the surface. That is very true. The potential energy at the bottom of the ball, not at the top, at the bottom of the ball at release, when it is being released, or at the point of release, should be equal to the kinetic energy of the bottom of the ball just before striking the surface, or before hitting the surface. That is a simple explanation. So this one I will just use conservation of energy, and I will simply say mgh, so the loss in potential energy is going to be the gain in kinetic energy. Of course, initially kinetic energy will be 0. So m is, what is m? If the kinetic energy of the ball is 0.75 just before it strikes the surface, what is its kinetic energy just after it leaves the surface? So we are looking at, let's first find the mass here. So the mass is going to be equal to the kinetic energy, which is 0.75 just before it strikes the surface, divided by g, which g is 9.81 times the height, which is 72. So it has fallen through a height of 72 centimeters, so it will be times 0.72. So for my calculator, I have that as 0.75 divided by 9.81 times 0.72. So this is giving me 0.11. Let me just take 0.11. So the mass is going to be 0.11 kilograms. So that is the mass of the ball which is falling. Now the question is asking us to find the kinetic energy just after it leaves the surface. Of course, as it leaves the surface, it is going to lose kinetic energy as it gains potential energy. So I'll simply say that the kinetic energy after leaving the surface is equal to the potential energy of the bottom of the ball at the height of 37 centimeters. So kinetic energy after, because it's going to lose it, kinetic energy after leaving the surface should be equal to the potential energy of the bottom of the ball at 37 centimeters. That when it raises to a height of 37 centimeters. So I'm just going to use the same formula. So the kinetic energy is going to simply be equal to mgh again, where now the mass is 0.11 times g, which is 9.81, then times h. It raises to 37 centimeters, which is 0.37. So somebody will say, why have you said kinetic energy is equal to mgh? I said the kinetic energy after leaving the surface will be equal to the potential energy of the bottom of the ball at 37 centimeters. So that's why I'm saying kinetic energy is equal to mgh, because I'm finding the potential energy at the bottom of the ball at 37 centimeters. So this is going to give us a 0.11 times 9.81 times 0.37, which gives us 0.385 or approximately 0.39. So this is 0.39 joules. So the answer here is going to be B. A wind turbine has blades that sweep an area of 200 meters squared. It converts the power available in the wind to electrical power with an efficiency of 50%. What is the electrical power generated if the wind speed is 10 meters per second? The density of wind of air is 1.3. The density of air is 1.3 kilograms per meters cubed. Okay, this is also easy. So we have been given speed and density, we have the efficiency, and we have the area. Let's begin by finding the mass per unit time, or mass per second. So mass per second, I'll call it m over t. The mass per unit time, or mass per second, is going to be density times volume per second, that is volume over t. To be density times volume per second, that is the mass per second. So this one is going to be equal to, the density is 1.3 times the volume, this will be times the volume. We have the area as 200, then it moves, of course, velocity, volume per second, 10 meters per second. What is the electrical power generated if the wind speed is 10 meters per second? You notice that area times speed over time, times speed, is the same as area times distance over time, which is volume over time. So that is going to be, when I multiply area by speed, I get volume per second. So this is going to be times 200,000, then times 10. That is going to be the mass per second. So this is going to be equal to, I think 2 times 1.6 is 2.6. So this becomes 26,000. So this is going to be 26,000 kilograms per second. So that is the mass per second. Also note that the kinetic energy is equal to a half mv squared. And the power from the wind, is going to be equal to the energy over time taken. And the energy here is going to be kinetic, so it will be a half mv squared divided by t. But since I have m over t, so this is the same as a half m per second, or mass per second, times speed squared. So that is going to be the power from which is coming from the wind. But remember, only 50% of this is converted into electrical power. So only 50% of this is converted into electric power. So 50% is 0.50. So the power, because what is the electrical power generated if the wind speed is that? So we want power generated. So this power generated, remember it is going to be just 50% of what is coming from the wind. So it will be 0.5, that is the 50%, times a half, times m over t, which is 26,000, then times v squared, which is 10 meters per second. So this is times 10 squared, which is the speed. So I'll just press my calculator here, 0.5 times 26,000, then times 10 squared. There's another a half, which is going to be divided by 2. So I'm getting 650,000. So this is going to be 650,000 watts, which is 650 kilowatts. So the answer here is going to be B. The diagram shows a wheel of circumference 0.3 meters. A rope is fastened at one end to a force meter. The rope passes over the wheel and supports a freely hanging load of 100 newtons. The wheel is driven by an electric motor at a constant rate of 50 revolutions per second. Okay, when the wheel is turning at this rate, the force meter reads 20 newtons. So this one is easy. Let's just see the diagram. So if it makes one revolution, that is, remember the circumference is 0.3, and it is making 50 revolutions in 1 second. So in 1 second, the distance covered is going to be 50 times 0.3. That is the distance covered. And work done is equal to force times distance. Let's see what we want here. What is the output power of the motor? So we can find the net force here. The net force here. The net force is the one which is now going to cause the net force is the one which is going to cause the net force here is the one which is going to cause movement of this. So the net force is going to be the load, which is 100 newtons, minus the reading from the Newton meter is 20, so I'll say minus 20. So this means the net force is going to be 80 newtons. The net force on the system is 80 newtons. So I want to find the output power of the motor. Since I have in 1 second the distance covered is this, then it means the power is simply going to be equal to 80 times 50 times 0.3, because remember this is per second. This one is in meters, because this is distance in meters per second, which is actually velocity, which is actually speed, because in 1 second it makes 50 revolutions, but each revolution is 0.3 meters. So it means in 1 second it makes 50 times 10 power 3 meters. So that means this distance is the same as velocity. In 1 second it is making 50 times 0.3 meters. So meters in 1 second, that is velocity. So I will just say power is equal to 80 times 50 times 0.3. Or we just simply say force, which is 80 newtons times distance, which is 50 times 0.3. And this gives me 80 times 50 times 0.3, which gives me 1,200. So this is 1,000. What's wrong with my pen? 1,000. Okay, so this, I said this is going to be 1,200. So this is 1,200 watts. Sorry for that. So this is going to be 1.2 kilowatts, which means our answer is going to be B. A light wave of amplitude A is incident normal on the surface of area S. The power per unit area reaching the surface is P. The amplitude of the light wave is increased to 2A. The light is then focused onto a smaller area, a third S. What is the power per unit area on the smaller area? Okay, let's go back to the relationship between intensity and amplitude. Remember, intensity is directly proportional to amplitude squared, which means doubling the area must increase the intensity. I think that is very true. And by what factor? Because intensity is directly proportional to amplitude squared, it means doubling the area, no, not doubling the area, doubling the amplitude. So doubling amplitude, it means it increases the intensity. It increases the intensity by a factor of 4, by a factor of 4, because intensity is directly proportional to amplitude squared. That means if the amplitude is now twice a but squared, it means the new intensity is going to be a constant into 4a squared. That means doubling the amplitude increases the intensity by a factor of 4. Number 2, intensity, or let me just say here initially, intensity is equal to a constant times a squared. Next will be intensity I2 will be equal to the a constant into twice a squared, which means intensity is equal to 4k a squared, which is the same as 4 times the initial intensity. So I2 is 4 times the initial intensity. So it means doubling the amplitude increases the intensity by a factor of 4. Number 2, intensity is inversely proportional to area. So a third estimate means we have decreased the area by a factor of 3. So I'm saying decreasing surface area by a factor of 3. By a factor of 3 increases, because they are inversely proportional, so it increases intensity by a factor of 3. Increases the intensity by a factor of 3. So intensity has increased by a factor of 4 because we have doubled the amplitude. It has also increased by a factor of 3 because we have decreased the surface area by a factor of 3. That means the total intensity will now be the new intensity, or the overall increase. Overall, let me call it overall increase in intensity. The overall increase in intensity is going to be 3 times 4, which gives us 12. So the intensity increased by a power or a factor of 12. But also remember, intensity is directly proportional to power. So it means the power per unit area reaching the surface is P initially. So that means the intensity is going to be actually 12 times P. So next time it will be just C. It will be C. So our new intensity, the new power per unit area, let me just say the new power per unit area will be equal to 12 times the first power that we had. Because the intensity is intensity is the power per unit area. If you didn't know, intensity is equal to power per unit area, but intensity is directly proportional to amplitude squared. So that means our answer is going to be 12 times the original power per unit area. A spring of an extended length 40 millimeters is suspended from a fixed point. A load of 16 Newton is applied to the free end of the spring. This causes the spring to extend so that its final length is 5 times. Its final length is 5 times its original length. The spring obeys Hooke's law. The spring obeys Hooke's law. What's the energy stored in the spring due to this extension? So we know that energy stored is equal to a half times the force times the extension. And the extension x is equal to, because it extends to 5 times its original length, if the original length is L, the new length is going to be 5L. So the extension is going to be 5L minus L, which is 4 times L, which is going to simply be 4 times the unstretched length, which is 40 times 10 power negative 3. That is going to be the extension. So the energy is going to be a half times 16 times the extension, which is going to be 4 times 40 times 10 power negative 3. So I'll check with my calculator. So this is going to be a half, that is 0.5 times 16 times 4 times 40 exponent negative 3, which gives us 1.28. So this energy is 1.28 joules, which is approximately 1.3 joules. So the answer is going to be A. The diagram shows an arrangement used to find the output power of an electric motor. The wheel attached to the motor's axle has a circumference of 0.5 meters, and the belt which passes over it is stationary when the weights have the values shown. So the belt is stationary. The belt which passes over it is stationary when the weights have the values shown. So that means we need the net force here is the most important thing. When we look at that, the net force is going to be 50 minus 20, which is going to be 30 newtons. And the distance moved. The wheel attached to the motor's axle has a circumference of 0.5 meters. And the belt which passes over it is stationary when the weights have the values shown. If the wheel makes 20 revolutions, so that means the distance in 1 second, or which can be considered to be the speed. So the distance total distance is going to be 0.5 times 20 revolutions, that is meters per second. So distance is going to be equal to, I think this is 10 meters, but this is for 1 second. Distance moved in 1 second. So time is going to be 1 second. So I will say power is equal to work done over time taken. And work done will be the force, which is 30, times the distance, which is 10, over time, which is 1 second. Or I'll just say power is force times velocity. Remember, the number of revolutions per second times the distance will give us velocity. So this gives us the same thing. And this is, I think, 300 watts. So our answer is going to be A. What is the internal energy of a system? Although internal energy is in A level, we can still answer it here. Internal energy is the sum of kinetic and potential energy. So it is the random energy of the atoms of the system, the amount of it supplied to the system, total kinetic energy of the system. It also involves potential, total potential energy of the system. It is both potential and kinetic. So the answer is going to be B. The random energy of the atoms of the system. This involves kinetic and potential energy of these atoms. So the answer is B. The diagram shows a barrel of weight 1 times 10 power 3 newtons on a frictionless slope inclined at 30 degrees to the horizontal. A force is applied to the barrel to move it up the slope of constant speed. So a force is applied to move the barrel at constant speed. That means the force upwards must be equal to the component of the weight down the slope, and this will be 1 times 10 power 3. When I resolve along the plane, that is going to be sine of 30. So what is the work done in moving the barrel a distance of 5 meters up the slope? So work done is going to be force times distance. The force is 1 times 10 power 3 sine of 30, then times the distance, which is going to be 5.0. So we just check with our calculator. 1 exponent 3 times sine of 30, then times 5, which is 2,500. So this is 2,500 joules. That means the answer is going to be A. A car traveling on a level road at a steady 20 meters per second against a constant resistive force develops a power of 40 kilowatts. What's the magnitude of the resistive force? So power is force times velocity. So we have 40,000 is equal to the resistive force times 20. So we just divide that one. I think 40,000 divided by 20 is most likely or most probably 2,000. So the answer is C. A turbine at a hydroelectric power station is situated 30 meters below the level of the surface of a large lake. The water passes through the turbine at a rate of 340 meters cubed per minute. Okay, that is per minute. The overall efficiency of the turbine and the generator system is 90%. What is the output power of the power station? So the efficiency is 90%. So efficiency, which is 90%, that is 0.9, must be equal to the power output divided by the power input. Divided by the power input. But what is the total power input? So the total power input will be to pump the water or to the water passes through the turbine at a rate of 340 meters cubed per minute. So it will be now the work done by the water, or the total work done by the water which is passed all over the turbine. So this is going to be power input is going to be the mass mg times the height over which the water is going to be falling. That is the energy input, the loss in gravitational potential energy, then divide by time. But remember, we don't have the mass, however, we have the volume. So mass is going to be density times volume. Then I'll divide this by T. They gave us per minute. So this is going to be volume times G times H. Then I'll divide this by T. Okay, since I have volume per minute, I will change it to volume per second. So I'm now just simply going to substitute here. So I will have that as 0.90 is equal to the power output divided by density, which is 1000. Volume is going to be 340, so that is times 340. But remember, it is per minute. I change it to per second, so I divide this by 60. Then times G, which is 9.81, then times H. The water must follow through 30 meters to reach the turbine. So the time V over T, I've already catered for it. So I'm just going to press my calculator to make a power out of the subject. So I have 0.9 times 1000 times 340 times 9.81 times 30 divided by 60. So that is 15, there's a 3, that is 1.5 times 10 power 6. So power out is 1.5 times 10 power 6 watts, which is going to be 1.5 megawatts. The pump of a water pumping system uses 2 kilowatts of electrical power when raising water. So this is the power input. The pumping system lifts 16 kilograms of water per second through a vertical height of 7 meters. So this work done is the power output. What is the efficiency? So efficiency is simply going to be power output divided by power input. The power output is going to be mgh over T, and the power input is 2 times 10 power 3. Then I will multiply this by 100. So m over T is 16 times G, which is 9.81, times H, which is 7, divided by 2 times 10 power 3, times 100 to make it percentage. So we have 16 times 9.81 times 7 times 100 divided by 2 exponent 3. So that is 5. What have I done? We have 16 times 9.81 times 7 times 100 divided by 2 exponent 3. That is 54.936, which is 55%. So this is 55%. So the answer is going to be D. A body traveling with a speed 20 meters per second has kinetic energy EK. If the speed of the body is increased to 80 meters per second, what is its new kinetic energy? I think this is direct. So kinetic energy is a half mv squared. So for the first one, we shall say EK is equal to a half times m times 20 squared. For the second one, I'll call it E2 is equal to a half. It is the same body, so times the mass times the speed, which is 80 squared. So now divide these two. I want E2, so I'll simply say E2 over EK. A half m will cancel when I divide, so this will be equal to 80 squared divided by 20 squared. So 80 squared divided by 20 squared gives us 16. So E2 is going to be 16 times EK. So the answer is going to be D. A concrete cube of side 0.6 meters and uniform density 2 times 10 power 3 kilograms per meters cubed is lifted 5 meters vertically by a crane. What is the change in potential energy of the cube? So this one is direct. Potential energy is equal to mg times the change in height. They didn't give us the mass, but mass is density times volume. So this will be times g times the change in height. The density is 2 times 10 power 3. Then V is, what is V? It is a cube. Oh, it is a cube. So V is 0.6 times 0.6 times 0.6. So it will be 0.6 cubed times G, which is 9.81. Then times H, which is 5. So because it is a cube, the volume, all sides are equal. So the volume is 0.6 cubed. So this will be 2 exponent 3 times 0.6 cubed. Where is cubed? 0.6 cubed times 9.81 times 5, which gives us 2, that is 189, which is 21 kilojoules. So this is approximately 21 kilojoules, which means our answer is going to be B. The force resisting the motion of a car is taken as being proportional to the square of the car's speed. So force is directly proportional to V squared. The magnitude of the force at a speed of 20 is 800. So I'll say 800 is equal to a constant times the speed of 20 squared. What effective power is required from the car's engine to maintain a steady speed of 40? So let's first find the force, which corresponds to 40. So F is equal to K times 40 squared. So what is F? We just divided two equations. So we get 40 squared divided by 20 squared times 800. So 40 squared divided by 20 squared times 800. That is 3,200. So the force required to maintain a steady speed of 40 is 3,200, but we want power. So power for that force is force times velocity, which will be equal to force 3,200 times the velocity, which is 20. No, it is 40. So 4 times 32. So that is 128,000. So this is 128,000 watts, which is 128 kilowatts. So the answer is C. The data below are taken from a test of a petrol engine for a motor car. Power output is 150. Fuel consumption is 20 liters per hour. That is the fuel input. So that means we can find power input as the fuel consumption, because it is energy, which is 50. Energy over time, that is power input. The energy, total energy is going to be 40 megajoules. That is 40 times 10 power 6. But remember, this is per liter and it takes in 20 liters. So it is 40 times 10 power 6, then times 20. But remember, per hour, that is per hour. So time is 1 hour. 1 hour is 3,600, which is 60 times 60. That is the power input. So which expression will evaluate the efficiency? So efficiency is equal to power output divided by the power input. So the power output is 150 times 10 power 3. When we divide, we get the reciprocal, so it becomes times 60 times 60 divided by 40 times 10 power 6, then times 20, which means our answer is going to be automatically B. What is the internal energy of an object? I said internal energy is invariable, but you can still answer it here. The sum of the random distribution of the potential and the kinetic energy of all the molecules or atoms which make up the system. That is internal energy. So the answer is going to be D. It's the sum of all the microscopic potential and kinetic energies of the molecules in the object. Or that is internal energy. Energy associated with the random movement of the molecules in the object. Energy associated with the object's movement through space, that is obviously not making sense. Energy due to attraction, that is not making sense. It is the sum of kinetic and potential energies of all the molecules. A car engine exerts an average force of 500 newtons in moving the car 1 kilometer in 200 seconds. What is the average power? So power is equal to work done over time taken. The work done is force times distance, then divide by time. The force is 500 newtons times the distance is 1000 because it is in kilometers, divided by the time, which is 200 seconds. I think this is automatically is it that 2.5 kilowatts? 500 times 1000 divided by 200. So this is going to be 2500 watts, which is 2.5 kilowatts. A car traveling with the speed 28 meters per second leaves a motorway on an exit road. The end of the exit road is 20 meters higher than the motorway. If only the force of gravity is considered, only the force of gravity is considered, what will be the speed of the car at the end of the exit road? Okay. So initially it is moving with the 28 meters per second. Now the change in kinetic energy should be equal to the change in gravitational potential energy. So the change in kinetic energy, that means it will be losing kinetic energy, I think, because it's moving to a higher ground. The change in kinetic energy will be equal to the change in gravitational potential energy, or the loss in kinetic energy will be equal to the gain in potential energy. So for kinetic energy, it will be a half times the mass, which is m. The final speed or the initial speed is 28 because it's higher, 28 squared minus the final speed, which is going to be v squared, should be equal to the change in potential energy, which is mgh. So the mass is m, then times g, which is 9.81, then times h, which h is 22. So m cancels out. I'm going to press my calculator to find the v. So I have 9.81 times 22 on the right hand side, then I multiply this by 2, that is a half on the left hand side, then I will say 28 squared minus the answer, 28 squared minus the answer. I'm making v squared the subject. That's what I have. Then I find the square root of the answer. I'm getting 18.77. So v, after finding the square root, is 18.77. So that means v is approximately 19. So the answer is going to be B. A piston in a gas supply pump has an area of 400 centimeters squared and it moves a distance of 25 centimeters. So the volume is going to be this times that. Cross-sectional area times the distance it moves. The pump moves the gas against a fixed pressure of 3,000 pascals. How much work is done by the piston during one stroke? So work done is equal to pressure times change in volume. The pressure is 3,000. The change in volume is going to be 400 times 25, that is in centimeters cubed. So I'll multiply by 10 power negative 6 to change it to meters cubed. So this is going to be 3,000 times 400 times 25 exponent -6, which is 30. So this is automatically 30 joules. So the answer is going to be A. A transformer has the following input and output. So input V is 11,000, current is 28. Output V is 240 and I is 1,200. What is the efficiency? I think this is direct. Efficiency is equal to P out divided by P in times 100%. And remember, power can be I times V. So power output is going to be 240 times 1,200 divided by 11,000 times 28. Then I will multiply this by 100 to change it to percentage. So this will be equal to, open brackets, 240 times 1,200 divided by, open brackets, 11,000 times 28. Then I multiply this by 100, which gives us 93.5, that is approximately 94. So this is 94%. So the answer is going to be D. The kinetic energy of a particle is increased by a factor of 4. By what factor does its speed increase? We know that kinetic energy is equal to a half mv squared. So it means when the kinetic energy is 4 times ek, this will be a half m times the speed, I'll call it v2 squared. So I just divide the two equations. So I have that 4 ek divided by ek is equal to a half m has cancelled, so this will be v2 squared over v squared. So ek has cancelled. So it means v2 squared is equal to 4 times v2. Then I find a square to both sides. So it means v2 is equal to twice v. So it means by what factor does its speed increase? So the answer is automatically 2. There is a 2 in front of v. A piston in a gas supply pump has an area of 600 centimeters cubed and it moves a distance of 40 centimeters. So the volume is 600 times 40. The pump moves the gas against a fixed pressure of 5,000 pascals. How much work is done by the piston during one stroke? So we have just done this. Work done is pressure, which is 5,000 times change in volume, which is going to be 600 times 40. Because it is in centimeters cubed, I'll multiply by 10 power negative 6 to change it to meters cubed. 5,000 times 600 times 40 exponent negative 6. That is 120. So the work done is 120 joules, which makes the answer to be 1.2 times 10 power 2 joules. A railway engine accelerates a train of total mass 800 tons. 1 ton is 1,000 kilograms from rest to a speed of 50 meters per second. How much work must be done on the train to reach this speed? So work done is going to be the change in kinetic energy. Work done is equal to change in kinetic energy. So this will be a half times the mass, which is 800, times 1,000 times the speed, which is 50, and this is squared. So for my calculator, I have 0.5 for a half times 800 times 1,000 times 50 squared. So this is 1 times 10 power 369. So this is 1 times 10 power 9 joules. So the answer is going to be C. Water from a reservoir is fed to the turbine of a hydroelectric system at a rate of 500 kilograms per second. So this is mass over time. The reservoir is 300 meters above the level of the turbine. So this is the height h. The electrical output from the generator driven by the turbine is 200 amperes at a potential difference of 6,000 volts. So this is going to be the power output. I mean, it is going to give us the power output What is the efficiency of the system? So efficiency is equal to power output. Power output is going to be I times V. So this will be 200 times 6,000. The power input will be now moving the turbine, or the reservoir is 300 meters above the level of the turbine. So water from the reservoir must be fed to the turbine. So moving that water is the energy input. So this is going to be the power input. I'll say power input is equal to energy over time, which will be mgh over t, and I have m over t. So this is going to be 500 times g, which is 9.81, times h, which is 300. I'll multiply by 100 to change it to percentage. So I have 200 times 6,000 times, of course, again 100 to change to percentage, divide by 500 times 9.81 times 300. So this is giving me 81.5, which is approximately 82%. So this is 82%. So my answer is D. A piston in a gas supply pump has an area of 500 centimeters squared and moves a distance of 30 centimeters during one stroke. The pump moves the gas against a fixed pressure of 4,000 pascals. How much work is done by the piston? This is a similar question. So work done is pressure, which is 4,000, times the change in the volume, which is 500 times 30, but we change this to meters cubed by multiplying by 10 power negative 6. So 4,000 times 500 times 30 exponent negative 6. That gives us 60. So this is 60 joules. So my answer is going to be A. A railway engine accelerates a train of total mass 1,200 tons from rest to a speed of 75 meters per second. How much useful work must be done on the train to reach this speed? So work done is going to be equal to the change in the kinetic energy. So this is going to be a half. The mass is 1,200 times 1,000 to change it to kilograms. That is mass. Then times v squared. So times 75 squared. So 0.5 times 1,200 times 1,000 times 75 squared. So this is giving me 3, that is 3 zeros, 3.4. 3.4 times 10 power, are they 6? Let me check. No, they are not 6, they are 9. 3, 6, 9. So times 10 power 9. So the answer is going to be D. The answer there is D. A crane is being used to lift containers off a ship. One container has a mass of 14,000 kilograms and is being lifted vertically with a speed of 3.2 meters per second. The electric motor being used to supply the power to lift the container is using a current of 240 amperes at a potential difference of 2,200 volts. What is the efficiency of the system? What is the efficiency of the system? So the power output is, of course, the electrical motor being used to supply the power to lift the container is using a current of 240 and a potential difference of 200. So this is going to be the power input. Power input will be I times V, which is 240 times 2200 volts. That is the power input. Then the power output will be a crane is being used to lift containers off a ship. One container has this mass and is being lifted vertically. So this is the work done. The power output is here. So the power output will be mg, which is the force, times the velocity v. So this is going to be mg, which is the force, that is 14,000 times 9.81, because we are overcoming that velocity, that mass, that weight, then times the velocity, which is 3.2. So let's find the efficiency now. So efficiency is going to be the power output, which is 14,000 times 9.81 times 3.2 divided by 240 times 2200. I will multiply this by 100 to change it to percentage. So we can check. So this is 14,000 times 9.81 times 3.2, maybe times 100, divided by 240 times 2200, which gives us 83%. So this is 83%. Therefore, my answer is going to be D. Trains supply coal to a power station. The table below gives quantities describe the operations of the power station. Power station output is symbol is P, unit is watts. So the output is P, symbol in watts. Power output is equal to P in watts. Then number of trains per day is N. Mass of coal on each train on a train is M. Energy from 1 kilogram is J. And the number of seconds in 1 day is S. Okay, that is also easy. Energy input is going to be energy for energy from 1 kilogram is J times the energy from 1 kilogram of coal is J, but the total mass of the coal is M. So that is total energy for all that mass, but that is for just one train. But the number of trains is N, so this will be times N. That is the energy, total energy per day. But in 1 day we have S seconds, so we divide this by time of 1 day, which is S, to find the power. So sorry, energy is that, then power in is going to be J M N divided by time 1 day, which is S in seconds. So this is S. So it means the efficiency is going to be the power output, which is P divided by J M N, and the S goes up. So the answer is going to be automatically A. A steel sphere is dropped vertically onto a horizontal metal plate. The sphere hits the plate with a speed u, leaves it at a speed v, and rebounds vertically to half of its original height. Which expression gives the value of v over u? Which expression gives the value of v over u? Okay, so we are going to use simple equations of motion. A steel sphere is dropped vertically onto a horizontal metal plate. The sphere hits the plate with a speed u. It is dropped. Initial velocity is 0. So using v squared equals to u squared plus 2as. This time u is the final velocity when it hits the plate. So the final velocity is u squared. Initial is 0 squared. Because it's falling, this will be plus 2g. It has fallen through a distance h. The sphere hits the plate with a speed u. Leaves it at a speed v. Now when it leaves with a speed v. So initial velocity is now v. And rebounds vertically to half of its original height. So again, using equations of motion, initial velocity is this time when it is leaving, it is v. When it reaches maximum height, velocity becomes 0. So I will say 0 squared is equal to v squared when it leaves the surface. Because it is moving against gravity, I will put here minus. So this will be minus 2g, but now the height it reaches is half of the original. So this will be a half of h. So I now have two equations here. The first one is I have that u squared is equal to twice gh. The second one I have that v squared is equal to 2g times a half h is going to be gh. So I divide the two equations. V over u, v squared over u squared is going to be gh over 2gh, and gh has cancelled. Then I remove the square, so I get v over u is going to be the square root of 1 over 2, which is simply 1 over root of 2. So that means the answer here is going to be precisely C. A block of mass 2 kilograms is released from rest on a slope. It travels 7 meters down the slope and falls a vertical distance 3 meters. So it has mass 2 kilograms. It falls 7 meters down the slope. The block experiences frictional force parallel to the slope of 5 newtons. So the friction is 5 newtons. What is the speed of the block after falling this distance? So it loses potential energy as it does work against friction and gains kinetic energy. So I will simply say loss in potential energy should be equal to the work done against friction plus the gain in kinetic energy. So loss in potential energy is going to be mg times the change in the height. The work done against friction will be force times the distance plus the change in kinetic energy, or plus the gain in kinetic energy, Ek. Remember, it starts from rest. So this is going to still be very easy. So let's find the gain or the change in kinetic energy, which will be mg. M is 2. Is the mass 2? Yes. G is 9.81. H is 3. Minus the work done against friction, which is 5. Force was 5 times distance, which is 7 along the plane. So this gives us the kinetic energy. So remember, kinetic energy is a half mv squared. So a half mv squared is equal to 2 times 9.81 times the 3 minus 5 times 7. So that is 23 point, is it 23? 2 times 9.81 times 3 minus 5 times 7, 23.86. So this is 23.86. That is the kinetic energy, 23.86. So I want to find V because I want the speed after it has fallen. So V is going to be the answer times 2. I divide by the mass, which is 2 again. I find the square root of the answer, which is 4.88 or 4.9. So V is going to be 4.9 meters per second. So the answer is going to be A. A man has a mass of 80 kilograms. He ties himself to one end of a rope which passes over a single fixed pulley. He pulls on the other end of the rope to lift himself up at an average speed of 50 centimeters per second. What is the average useful power at which he is working? So of course, power is going to simply be force times velocity. But the force is going to be overcoming his weight. So the force is going to be mg times v. So this is going to be the mass, which is going to be 80 times 9.81, then times v, which is 50, but note it is in centimeters per second. So I'll multiply by 10 power negative 2 to change it to meters per second. So this is 80 times 9.81 times 50 exponent negative 2, which gives me 392, or approximately 390. 390 watts in kilowatts is 0.39 kilowatts. I divide by 1000, 0.39 kilowatts. So the answer is going to be B. A body traveling with a speed of 10 meters per second has kinetic energy 1500 joules. If the speed of the body is increased to 40 meters per second, what is its new kinetic energy? So this is also easy. Initial kinetic energy is 1500, and this is equal to a half times the mass times v, which is 10 squared. Then we want the new kinetic energy Ek, which is a half times the mass times the new velocity, which is 40 squared. So I just divide the two equations. Ek over 1500 will be equal to a half m was cancelled. So I have 40 squared over 10 squared. So 40 squared divided by 10 squared is 16 times 1500, which is 24,000. So Ek is going to be equal to 24,000 2000 joules. So the answer is going to be C. An electrical motor produces 120 watts of useful mechanical output power. The efficiency of the motor is 60%. Which row is correct? So we know that efficiency should be equal to P out divided by P in. The efficiency is 0.60%, I mean 60%, which is 0.6. So um, the output is 120, so I will say here it is 120. 120 divided by power input. So what is the power input? I have 120 divided by 0.6. The power input is equal to 200. So power in is 200 watts. So I eliminate A and B. Then the power waste heat power. So power wasted or power loss is going to be 200 minus 120, which is automatically 80 watts. So the answer is going to be D. A hammer with 10 joules of kinetic energy hits a nail and pushes it 5 millimeters into the plank. Both hammer and nail come to rest after the collision. What is the average force that acts on the nail while it moves the 5 millimeters? So we shall just use work done is equal to force times the distance. We want the average force. The work done is the gain in kinetic energy, which is 10 joules, is going to be equal to the force times 5 times 10 power negative 3 to change it to meters. I think when I make F the subject as 10 over 5 times 10 power negative 3, I think this is automatically 2000 newtons. So the answer is going to be D. The first column in the table gives 4 examples of work being done. The second column gives more detail of the action. Which row is not correct? A girl dives from a diving board into a swimming pool. That is the example. Detail. Work is done by. This makes this one to be wrong. Because diving is falling downwards, work is not done by the girl against gravity. It is actually gravity doing work on the girl. So this one is not correct. A man pushes a car along a level road. Work is done against friction because there is a force, and the level road we expect it to be rough. Work can be done against friction. That is correct. An electron is accelerated towards a positively charged plate. Work is done on the electron. Yes, because it's moving towards a positive plate, then work is done on the electron by the field, not work being done by the electron, because if this is a positive plate and negatively charged particle naturally moves in that direction. So it means the field is the one which is doing the work on the electron, not the electron doing work, or not the work being done by the electron. A piston is pushed outwards as gas expands. Because the piston is pushed outwards as the gas expands, it means work is done by the gas. So work is done by the gas. This is correct. So what is not correct is A. Okay, so I think let part 4 stop there. See you in part 5. Part 5 will start from page 61, and it will be the last part. Part 5 will be the last part. I hope you have learned something from these videos. Enjoy your day and bye bye.